So remember I was telling you that identities and equations, that's usually the hardest part, right? So now we're moving into polar coordinates, okay? And then we're gonna do law of signs and cosines, right? Nobody ever really has too much of a problem with those processes. So we're kind of on the downhill slope for the trig, if that's concerned. And I do think that this is kind of fun. I had found a battleship game at one point where you could play battleship using polar coordinates, which I thought was kind of fun. But when we think about polar coordinates, the way I like to consider polar coordinates is if you are, let's pretend that you're a submarine, okay? And that you extend your periscope up, all right? And now I can look in 360 degrees, right? I can turn this periscope 360 degrees. So I'm gonna rotate around in some direction, either positively or negatively, from a central point in the center of, in my ship, right? So I'm gonna rotate and I'm gonna locate the ship I want to fire on. I'm playing battleship in my head, right? So I'm gonna rotate my periscope until I identify the location of the thing I want to sink. And it's at that point that I'm now going to shoot something, right? I'm going to launch my whatever, and I'm going to go straight towards the thing I want to sink. All right. So I'm going to rotate first, and then I'm going to figure out what the direction or what the distance is from the center. Okay. And another way, because it's sometimes the negative values, another way would be if I rotate around, right? So, and then I want to shoot behind me. Okay, so going forward would be a positive distance, right? That would be a positive value of R, right? R is our distance from the center. Going negatively would be behind me, right? When R is negatively, I think about walking backwards. So when I'm looking at my points here, like in that point right there, -3 pi over 4, R is the distance from the center to the location of what I'm looking at, where the point. And pi over 4 is how far I had to rotate around it. So if I rotate to pi over 4 first, all right, so I'm here at pi over 4, and there I'm at pi over 4, I'm still standing here at the center. All I do is rotate pi over 4 or 45 degrees. But now I'm going to move backwards by a distance of 3. Okay, does that make sense now? Yes? Okay, hold on a second. Really? Yeah. Okay, what?
So what if your data is negative?
Rotate first. So if I rotate negative pi over 4, right, I'm down here. And if I still have to walk backwards, -3, I would be up here.
Oh,
Okay.
okay, it makes better sense.
All right. So I always think of it as this rotation first, and then I'm either going to walk forward positively because I haven't moved from the center. The center is just me rotating this periscope around. All right. It's rather childish, but it's the way that I'm thinking of it. And then I'm either going to walk straight toward it as a positive direction, or I go backwards in the negative direction. Okay. Does that help a little bit? So polar coordinates is what we're talking about, obviously. Okay. Now I'm going to give you a chance to practice these in a minute. Let me make sure that they're not. Well, we could look at these for a second.
It's something different.
These were the 2 and 135? The exact one? All right, we did all right then.
Yeah. I think so.
And the -1, negative pi over 2?
Yes, ma'am.
All right, well then good, you did it already. Okay, so we're gonna move on, and I know those were on there as well, right? Representing it in 3 different ways. Representing where R is positive, yet I'm gonna constrain theta to be between 2 and 4 pi, okay? R would be negative, but I now want to talk about theta between 0 and 2 pi positively, or R is positive and I want to look at a negative angle. Okay, so these are not the only ways for us to be able to represent a point. We can go around and round and round or whatever, but these are the three that we are kind of focusing on. Okay. So that brings us then, once you kind of understand the polar coordinate system, we want to be able to convert from one system into another system. So we're talking about rectangular versus polar coordinates. And it uses trig. Okay, this is why it follows along with that. So the rectangular coordinate system and the polar coordinate system are related in this fashion right here. We know this already, but just make sure that you write it down because it's helpful to have this kind of in front of us. So x from the rectangular coordinate system is equal to r times the cosine of theta in the polar coordinate system. And that comes from our definition of cosine. Y is equal to r sine theta. Again, that's our definition of sine. To find r, we've been doing this all along. That would just be the hypotenuse of our triangle, because this is right triangle trigonometry that we're looking at here. So x squared plus y squared is equal to r squared. And then we know that tangent theta is equal to y over x. So those are the conversions that we're going to use to be able to convert between the two systems. And all of that is stuff that we were familiar with. So nothing in here is really new. And the first thing that I want to do is I want to convert from polar into rectangular. In other words, when I'm looking at an ordered pair in a polar system, I've got r's and thetas. When I look at an ordered pair in the rectangular system, I've got x's and y's. So in this particular case, the example we're looking at here says that I've got 3 and pi. Those are both in the polar system, or that's the polar system right there. And I want to convert this into the equivalent rectangular coordinate system. So identifying out of that ordered pair that 3 is r, theta therefore has to be pi. And to convert this to the x coordinate, we know x is equal to r cosine theta. So in other words, 3 times the cosine of pi. What's the cosine of pi?
0.
-1? Yep, -1. And -1 times 3 would be -3. Y is equal to r times the sine of theta, or in other words, 3 times sine pi. Now what's the sine of pi? 0. So this would be 0. Therefore, the ordered pair in the rectangular system is -3, 0.
That seems easy.
This is pretty, once you recognize what formulas you're going to use, how to convert them, okay, let's do it. So you all do the next one. Convert for me, give me the exact value going from polar to rectangular of -10 comma pi over 6. So what do we get? My x coordinate would be -10 times the square root of 3 over 2. Or in other words, -5 square roots of 2. I mean, excuse me, -5 square roots of 3. If I simplify. And the y coordinate would be -10 times 1/2, or in other words, -5. So -5 square roots of 3, -5 is the equivalent rectangular form. Just using those the forms of our conversions we already know. All right, let's go backwards now. There's no questions on this one. Okay. So if I want to go in the opposite direction, now if I want to take something that is rectangular and convert it into its polar coordinates, right? I've got to take things and turn them into r's and thetas. Right, r's and thetas. Now this is actually going to look a lot like what we were doing before with our in our trigonometry. And so when we are looking at this point here, I'm just going to kind of quickly sketch the point 1 negative square root of 3, which would be somewhere down here. I know I've traveled 1 in the horizontal direction. I know I've traveled negative square root of 3 in the vertical direction. And so remember, we're trying to turn this into r's and thetas. So the first thing I need to know is what r is. So x is equal to 1. Y is the negative square root of 3. R is going to be x squared plus y squared, which would be the 4, and the square root of 4 is 2. Okay. So x squared plus y squared, so 1 squared plus negative square root of 3 squared gives me 2. So now I know what r is, obviously, and I'm now thinking, see, that would be a 2 here, and I'm now thinking, okay, to find theta, I need to know the tangent of theta is equal to y over x, which would be negative square root of 3, that's right. So what angle, when I take the tangent of it, do I get negative square root of 3?
Square root of 3 over 2. What angle?
So what angle, when I take the tangent of it, do I get the square root of 3?
Pi over
Negative
3.
5 pi over 3.
Oh, yeah,
That's right, 5 pi over 3, if that's what you said over there. So the equivalent polar coordinate is going to be 2 for r and 5 pi over 3 for the theta. So think about that for a second. We are rotating around the circle, and then we are moving a distance out to a point. Rotate and then fire. Okay. Let's try the next one, 0, negative 4. So 0, negative 4 would be down here.
Oh, so you just plot it like normal.
I don't have to do a whole lot with this one if I'm thinking about it, right? What's the distance from the origin to the point? What's r? 4, right? That's all, that's 4. And what would theta be then to rotate around to that spot? 3 pi over 2. So that would be 4, comma, 3 pi over 2. Quadrantal, that's pretty easy.
But wouldn't y over x be negative 4 over 6?
So that's going from rectangular to polar. It's going rectangular to polar. And that's all we're doing here in this section, is really moving from taking an equation in one form and converting it into another form. So that's the points that we're looking at there. Now let's do equations. Let's see if we can take an equation and convert it into its polar equivalent. Now I know I'm in rectangular because these are x's and y's, and I have to come up with an equation that is r's and thetas. All right, so the first one that I'm looking at over here, 3x minus y is equal to 6. I want to take all those x's and y's and turn them into r's and thetas. Remember that from above, we know that x is equal to r cosine theta and y is equal to r sine theta, right? We've already said that from above. So I'm going to replace x with r cosine theta. And I'm going to replace y with r sine theta. And that's equal to 6. So 3r cosine theta minus r sine theta equals 6 is what I have. And is there something that's common there that I could factor out?
The R's?
R. So I'm going to take r and I'm left with 3 cosine theta minus sine theta equals 6. And now what? Trying to get r by itself, so I would do what?
No.
Divide by the coefficient, right? Divide by 3 cosine theta minus sine theta.
Wouldn't R be the coefficient though?
R is a variable, and so whatever is there in the parentheses is kind of the coefficient
Oh,
in essence.
Okay.
3 cosine theta minus sine theta. So 6 divided by that denominator is 3 cosine theta minus sine theta. That's the equivalent polar coordinate, polar equation. Okay, did I miss something?
Oh, let's see.
Did I get it right? Did I subtract right? Nothing looks strange, right?
Wouldn't it be simplified because it's 6 over 3?
I can't simplify unless I can simplify both of those. So I would have to have maybe another 3 or another 2 in that second term to be able to cancel that. It has to go into everything. Okay, so that wouldn't work. Now, let me point out to you for just a second. Go back to the rectangular equation that we started at. What type of a graph would that look like? What is that? 3x minus y equals 6. What kind of a function is that? Come on, you know what this is. It's linear, right?
Linear.
X is raised to the first power, so it's only linear, right? It's just not in the y-intercept form. All right, so it's a line, right? 3x minus y equals 6 is a line. R equals 6 divided by 3 cosine theta minus sine theta is still going to graph a line. It just looks different, right? It's just a different representation. One's polar and one's rectangular. So look, if you graph both of these, it's going to be still a straight line or a slanted line. How about this one here? We have x squared plus quantity y plus 1 squared equals 1. We're going to take that and convert it into r's and thetas. Same process. So x is r cosine theta, and I'm going to square that, plus r sine theta plus 1 squared equals 1. So we have some expansion to do right here. We've got to take this first term, and I'm going to end up with r squared cosine squared theta plus, now here I'm going to expand that binomial, right? Square the first, double the product, square the last. You see how often we use this concept? That's why it's easy to, it's helpful to remember this one. So I've got r squared sine squared theta. I'm gonna square the first. I'm gonna double the product, so I get 2r sine theta. And I'm gonna square the last. And all of that's still equal to 1. Now let's see if we can combine any terms and simplify and so forth. So I have r squared cosine squared theta plus r squared sine squared theta plus 2r sine theta, and I'm going to subtract the 1 to the other side to get rid of it. So I only have variables now on the left-hand side. And let's do a little grouping kind of here.
Couldn't you also group the R squares?
Mm-hmm. Okay, so let's kind of focus on this over here, and I'll just put it in parentheses for us for a second. If I'm only talking about this that I put in parentheses, is there anything common between those two terms that I could maybe factor out? All right, so I would end up with r squared times cosine squared theta plus sine squared theta plus the 2r sine theta I already had. Okay, what is cosine squared plus sine squared? 1. Okay, because that is an identity. Leaving me with r squared plus 2r sine theta is equal to 0. Now here I could, and I guess I could have before too, I can factor an r out of both of these, and I'm left with r times 1 plus 2 sine theta. Excuse me, I'm left with r times r plus 2 sine theta is equal to 0 when I factor an r out of both of those terms, right?
So what we have to do the same thing we did the last time and just divide the R plus 2 sine theta?
No, I've got two factors that are now equal to 0, so I'm going to set each of these factors equal to 0 and use the 0 product rule. So I've got r equals 0 here, and I have r plus 2 sine theta equals 0 here. Now, think about this for just 1 second. R theta, R equal to 0, R is kind of like that distance away from the origin, isn't it? And so I'm at the origin, okay? So this root right here is kind of considered a repeated root. It's not getting me anywhere, so it actually disappears. R equals 0 is not needed in this particular case. We can move on, however, because it, like I said, is considered to be a repeated root at the origin. But for this right-hand equation, when I solve it, I would say r is equal to negative 2 sine theta. And I've now put the equation into r's and thetas. Okay? And it's a repeated root. If you were to substitute 0 in for theta, I believe that you would get 0 again as well in that spot. Yes, sir?
Wouldn't that be one of the identities we learned yesterday?
No, though you're thinking of a double angle. So that would be, the 2 has to be on the inside next to theta
Oh,
for it to
okay.
be a double angle. So the equation in polar form is -2, r is equal to -2 sine theta. Does anybody know what the original rectangular equation is? What is that function that we started with? Does anybody know?
X squared plus y plus 1 squared.
It's a circle.
Circle.
Yeah, it should be a circle. Yep. It's a circle. X squared plus y squared equals r squared is a circle. Okay, it's a circle that has a shift in it. So the +1 added to the y shifts our circle up. Actually, it's a vertical shift. It's shifting the origin or the center. Excuse me. It shifts the center, and it has a radius of 1. So what looks like that in the rectangular coordinate system is going to still graph to be a circle in the polar coordinate system down here, -2 sine theta. Okay. This will look totally different, don't they? Yep. Okay. I'll show you what these look like in just a minute, but this is the conversions that we're working on. So this is the idea behind polar, rectangular to polar is take everything and turn it into R's and thetas. And we're going to do it generally using these X is equal to R cosine theta, Y is equal to R sine theta. So now let's go in the opposite direction. So I want to take everything that's an R and a theta, and I want to turn it into the X's and Y's. And all I did was rewrite our conversions for us right here so that we would see them easily. So this says R is equal to 4. And for this one, remember that we've got to take what we have and turn it into X's and Y's. All I have is all I have is an R here. So what I'm going to do is I'm going to square both sides. When I square that, I end up with R squared is equal to 16. And I know that R squared is equal to X squared plus Y squared, which is equal to 16. And I'm done. That's it, right? I took the original and wrote it in terms of X's and Y's. That one was pretty simple, but you had to square both sides, okay, to get it into the R squared form. Let's look at this next one. Theta is equal to 3 pi over 4. Theta is equal to 3 pi over 4. The only thing I've got up here is the tan theta, which is equal to y over x. So let's take the tangent of theta. Let's multiply, in other words, both sides by tan theta, or by tan, excuse me. Multiply both sides by tan. That gives me tan theta on the left equal to, what is the tangent of 3 pi over 4?
3 pi over 4, wouldn't it be,
Square root of 2 over 2.
It's -1, so it's a 4, so it's always going to be a form of a 1. We're in the second quadrant, so we would be at -1. Now, if I've gotten it to this point, I can substitute in what is tan theta. Remember, I'm trying to get this out of thetas, put it into X's and Y's. So y over x is equal to -1. And now multiply both sides by x, and I find y is equal to -x. So it's just a sloped line passing through the origin. Okay, so in both of those, we had to do something to it before I could just make the straight substitution. But that was kind of the goal. Let's look at this one right here. R is equal to -secant theta. I don't have a substitution for secant, but I do for cosine. So let's take this and rewrite it as R is equal to -1 over cosine theta. And now I'm going to multiply both sides by cosine theta because I know R cosine theta, which is equal to -1. I know R cosine theta is x. So x would be equal to -1. And that's it. I put it in terms of that. What type of a line do I have at x is equal to -1? It's just, well, that would imply a line, right? Straight line. Vertical line, right? Vertical x is equal to vertical lines, y is equal to horizontal lines.
So you don't have to find X and Y, just at the very least find one or the other. Well, if it's not possible to find Y, just find the X. Which is-
Just no thetas and no r's. All right, let's look at this one. So this one says r is equal to 10 sine theta. To get rid of r, let's go ahead and square both sides. No. I don't want to do that.
You die.
I lied. I want to multiply both sides by r. So this is going to give me on the left r squared, which is equal to 10 times r sine theta on the right. So on the left, r squared is equal to x squared plus y squared. And on the right, 10 times r sine theta, which is y.
And
Let me look how far we want to go with this. Because this is going to make a conic. This is going to be a maybe it's an ellipse. Maybe that other one was an ellipse and not a circle. Let me just look really fast because we skipped around here. And notice that the notes that I gave y'all, that I put on the internet, I tried to put the section number of them as well. So you'll notice that we went from doing chapter 5 to 6 and part of 10. I just wanted to make sure that I'm taking you in feeling the right direction. Yep. All right, so it'll be kind of a preview of what we're going to cover anyway. So we have this in terms of x squared plus y squared is equal to 10y, which is what we were kind of discussing. That's why I wanted to check it, see how much further we needed to go. But this is, we're going to take this equation and go a little bit further with it. And in this equation, I am going to take all the variables over to the same side. So I've got x squared, because I want to put it in its most simplest form. There we go. X squared plus y squared minus 10y is now equal to, leave a space here, is now equal to 0. Okay, so leave yourself a little gap right there. X squared plus y squared minus 10y is equal to 0. And what I'm gonna do is I'm going to try to transform this into just x's and y's. I need to put this into, you know how sometimes we had our general form of our linear equation a few minutes ago that was 3x plus y is equal to 5, and a lot of you didn't recognize the form of the equation right off the bat because it wasn't in a form that you are used to seeing, right? Okay, so what we're gonna do is we're gonna take this equation right here and we're gonna put it in another form that would be maybe a little bit more recognizable in the conics, in view of the conics, or in another type of form. So you think ellipses, right, eggs, parabolas, or hyperbolas is in essence what we're gonna try to rearrange this for. Now, notice that I have my variable x, there's nothing else that can go with it, and it's just an x squared term. But I have this y squared minus 10y right here, and that is 2/3 of a perfect square trinomial, isn't it? You know what a perfect square trinomial is?
X, what the,
X squared minus 10x plus 25 is a perfect square trinomial. And that factors into x minus 5 to the second power, right?
Mhm.
Okay, it is a perfect square trinomial because the first term and the last term are the perfect squares. The middle is actually twice, right? It's square the first, double the product, square the last, going backwards. I just factored it into that. So once again, this pattern that I keep referring to is used a lot in math. And so this perfect square trinomial will give us a binomial that we can factor like this, right? That's a binomial. So what I have here is 2/3 of this perfect square trinomial. How many of y'all remember solving quadratics by completing the square? It's hard, well, that's because everybody hates it, right? You learn it in factoring, which typically you do factoring in the 9th grade. You probably do completing the square again in algebra 2. If you didn't take pre-cal, you probably haven't seen it again, and it is just, it's like this little blurb. Oh, by the way, we can solve using completing the square because it will always work, but nobody remembers it. And then all of a sudden, bam, it's going to come back to haunt you when you get to calculus, because we'll be using it a bunch for certain things. So what we're going to do is we're going to force my 2/3 of my y's here into this perfect square trinomial by completing the square. We take half. We take half of this term. What's half of 10?
5.
And now we're going to square it. So half of 10 is 5, squared would be plus 25. If I add 25 to the left, I got to add 25 to the right.
So we would have x,
So now my y's can be factored into, so I have x squared plus the factoring of that perfect square trinomial is going to be y minus 5 to the second power is all equal to 25.
Oh.
This is the form you want to see it in.
So either
And we're
way,
done.
so that's a perfect square too. The one we just got, right?
It is, but I can't factor that one because of this plus sign right here. Okay. So what did we do? When we completed the square, let's remember what we do when we complete the square. So when we complete the square, we took -10 and divided it by 2, which was -5 that we then squared, and that's how we got 25. And this -5 is always going to end up being that term when you're factoring it. If you'll just write it off to the side or remember what half of b is, that's always going to be the number in that binomial. Always. All right. So this is what we looked at. Okay, now We don't graph these in this class. I'm gonna let y'all practice these on your own. But we don't graph these in this class. And in fact, I used to have a section, but we don't have time. I used to have a cool section where we would kind of get to see what these graphs look like. And so I want to just show you, because polar graphs are actually really kind of pretty, I think. So, and you can graph in your graphing calculator, I believe, and I don't do it, so I don't really remember, but I think you have to change the mode to be parametric, I believe. That is super easy to do it in Desmos. So here in Desmos, let me change this to arrows.
Change it to parametric, polar, and sequential.
Polar. And if you change it to polar, what will happen is if you go back to the y equals,
It changes it to R.
it is ours, yeah. But this is kind of fun because I can type these in here and it's a whole lot easier. So I can say R equals 10 sine theta. And yep, I was right, it was a circle. I was afraid it was an ellipse. It's a circle, right? Okay. And should be able to say x squared, oops, plus, what did we say, y minus 5?
Squared.
Is equal to 25. Same thing, isn't it? Okay. If I turn that off and turn that on, it's the same thing. Now that's not fun, that's not exciting, that's not pretty, but the ones that are fun and exciting are pretty are, let me show you another one that would be kind of fun. Let's do 1 minus 2 sine theta. Looks like a little, you said 2 sine theta? Yeah. Oh, look what happened when I changed that number. Right? So if it's 1, it looks like this. It looks like a heart. I had a classroom full of boys who said it looked like a butt. First thing they said. Okay, it looks like a butt. All right, so then I can change that number. What happens if I change it again? Those are cool, aren't they? And they graph really pretty in here. You can, if I change this, let's go back, I change that to a plus. See where the
Oh, it
butt
flips
ended?
it.
It's above, right? So the plus and the minus sign changes that. The 1 is just changing the, should just be changing the size, right? I think it changes the size of the petals too. So they're kind of cool, all right? Those are some of them. And there's no point in trying to figure out how to graph them by hand, because there's all sorts of cool technology that can do it. And they have all sorts of different names. But those are the graphs of parametric equation, or polar equations, I mean. Sadly, you don't see these again until Cal 3. That's when you're gonna see it. So you'll forget everything I'm telling you, but it'll be that back there hiding in your brain. You'll at least have been exposed to it. All right, so what I want y'all to do is practice these on your own, or with some classwork, in other words. Okay. Now we'll come back to that one in a minute, but what I want you to do, I've got, let's try to work through questions 3, 4, and 5 right here. Excuse me, 2, 3, and 4 first, and then I'll move it up. All right. You can work with a partner, you can work by yourself, I don't really care, but I would like for you to practice these questions 2 through 4 and check in with me as you get those questions answered. And we'll see how well you're doing on that.